Hey everybody, and welcome back. We are continuing with exponential functions. Let's dive straight into it and see what we're working on today. So today we're going to just recap on growth and decay formulas. We touched on this in our live classes this past week, but I want to go back into it again for any of you who are not there. Then we're going to look at some modeling questions. So modeling, remember, is just real life scenarios. So the biggest one that we see most often is compound interest, so financial formulas, and we're going to look at how we calculate those today. And then we're going to write exponential equations using regression. So this is a calculator function. It's not one that Desmos will do. You'll need your actual calculator to do this. Or you can Google some regression calculators online where they'll let you put in your data and it'll tell you what the regression is. I want you to be familiar with how to do it on your calculator because this is something that you will do a lot in the higher levels of math, whether you go down the stats or calc route. And it's just a good skill to be able to do anyway. So plotting a bunch of data and finding out what is that best line of fit for the data. So in our case, an exponential line of best fit. That's going to be a separate YouTube video that I've linked to, mostly because I just don't have a good way of getting a calculator up on screen right now. So if somebody else has made a regression video, it's fine. It does exactly what you need it to do. You will be able to watch that and answer any questions about regressions very easily. Essential questions for today. What does it mean when we say compound interest? So what is that? And then what are the compound interest, or what are the interest formulas? So simple interest, compound interest, and continually compounded interest. You need to know all three of those because a word problem will just say like, hey, use this formula, and it won't give it to you. Last video, we talked about just the basics of exponential functions, what the parent function was, what its characteristics were. So we've got a asymptote that the function is either growing towards or growing away from, depending on whether it's decay or growth. We looked at transformations of exponential functions, and we just kind of touched on what a function with base e was. And we'll see e come up again in continuously compounded interest, but still not doing a huge amount of work with it just yet. All right, so remember exponential growth, the b value is greater than 1. It's growing away from a horizontal asymptote. Decay, the b value is between 0 and 1, and it's growing, or it's decaying towards the asymptote. So this was the formula we got in our last lesson. So a times b to the power of x. We have a minus h and a plus k in there too if we want some transformations, but this is the basic one. When we talk about just kind of real life scenarios today, we're going to develop out that b value a little bit. So the growth or decay factor. You have the a value, which is your starting amount. You have 1, which basically is the original amount, plus or minus the rate of change. So are you adding a percentage? Are you subtracting a percentage from the original amount? That will be our growth or decay factor. And then to the power of t, because we're typically talking about time. So let's just dive straight into some models. The value of a sports car purchased for new for $45,000 decreases by 15% per year. So this is called depreciation of value. So cars are, I guess, objects that do not hold their value very well. So as the car gets older or more used, it loses value. And it's typically by about 15% of the value each year. So you see a bigger drop in the first couple of years, and then as the car gets older, it loses less and less value each year by a numerical standpoint. All right, so write an exponential function for the depreciation of this sports car. And I will say it depends on the make and model as well. Some cars hold their value much better, some do not. So you always want to look up these things, and that's why you use car buying guides when you do stuff like that. All right, so the starting price is $45,000. That's our a value. And the value of the car over time is going to be our end goal, our range, the output of the function. So 45,000, 1, it's going down, it's decreasing. 15% as a decimal is 0.15. And then to the power of t, there we go. Actually, I think I'm going to have another part. This might overlap. Okay, how much will the car be worth in 5 years? So, and there's another part as well. Yeah. All right, so I'm going to move this down quick. Should have put the whole question in there first. All right, so how much will the car be worth in 5 years? So v of t is equal to 45,000, 1 minus 0.15 to the power of t. In 5 years, so time will be 5, so it'll be v of 5. So we have 45,000, 1 minus 0.15 is 0.85, so I can just write that in now. So that means every year the car is going to be worth 85% of what it was. And sorry, t is 5. So this goes in our calculator, and then we just see, okay, what is the answer? So after 5 years, it is worth $19,996, or $966, I should say, and 74 cents. So your $45,000 car after 5 years is worth less than half of what you paid for it, which is the crazy thing about cars. Like, they do drop in value quite a bit. Now, the thing is, if you went another 5 years, it wouldn't drop over half again. It would be, maybe around 10,000 or something like that. Like, so it would be slightly above half. And then if you did another 5 years, it might be 8,000. Like, so the gap is going to get smaller and smaller each year, but the first couple of years is when a car loses a ton of its value. So my biggest advice to you guys is when you buy cars that are 2 to 3 years old. So it's taken that biggest hit already. It's still pretty new. And then if you hold it for 5 years and sell it again, you're not going to have lost as much value from your purchase. All right, part 2, when will it be worth half of its original price? So half of 45,000 is, what's that, 22.5. So 22,500 is equal to 45,000.85. Now this is the hard part because we don't know the value of t. That's what we need to solve for. There's no algebraic way of doing this without going into logarithms, which we don't know how to do yet. So this is one that we're going to solve by graphing for now. So you're going to get your graph out. You put a line in at 22,500. This is a badly drawn graph because it's a decay model, not a growth one. So on day 0, it's 45,000. Put in a line at 22,500, and we see it come down and decay. So we want to know, like, what is that point? So what's the value of t for that time when it reaches that value? So you put it in Desmos or in your graphing calculator. One line is the left side of the equation, one line is the right. If you're doing it in Desmos or your calculator, instead of t, you are putting in x. That is your independent variable. That's your domain. So try it out quick and then come back and see how you did with the answer. So I used my calculator, put them both in. This was y1, this was y2. You hit graph, you make sure you can see it. So if, just a quick reminder on using our calculators, if you can't see it, hit the window button and adjust your x and y windows, so the minimum and maximum. So I just did 0 for x and y, and then y I made sure it went over 45,000, so I did 50,000. And then x, I just went up to 20 because I figured, like, okay, it's probably not going to be more than 20 years for it to cut in half. And then I was able to see both and where they intersected. And to find that point of intersection, it's second function, trace. So the second button, trace button, and then it's option number 5, which is the intersect option. And then you use that to find your point. If you don't remember how to do that, just go into YouTube and type find point of intersection using TI and then whatever your model is, 83, 84, 85, whatever it is. And it will walk you through those steps. So the answer I got is x, or in our case, t, is equal to, just lost my answer there, 4.27 years. So 0.27, it's a little over a quarter, so a quarter of the way through the year. So in about 4 years and 3 months, somewhere like 3 months and a couple of days, the car will have dropped to nearly half of the value of what you paid for it. So if you think that most people will keep a car for 2 to 5 years, like you take a huge hit in the value of the car in the first couple of years. The longer you hold it, the more value you get from the car. So again, going back to car buying advice, buy a 2 to 3 to 5 year old car and then aim to hold it for 5 to 10 years. That will see you get the most value out of your car. And if you want to know more about that kind of stuff that interests you or excites you, highly recommend taking a personal finance class such as contemporary math. All right, new one. Tony purchased a rare guitar. So as soon as you see the word rare come up or collectible or something like that, it's not going to follow the same rules. And it's true with the car as well. If, say, we bought that car, sports car, and say it was like one of the classic Ferraris or something like that. In the beginning, it would have exponentially decayed, but then at some point it becomes a collector's item and it starts to go back up again. And it may not grow as fast as it decayed, but it does get back to being worth something again. And a lot of times some of these cars are worth more than what they were new because they are much more rare at the time. So for example, like buying a DeLorean, you'll pay way more for it now for a collector's DeLorean than you would for when it was brand new, just because it is such a rare thing and an iconic car as well. All right, so rare guitar in 2000 for 12 grand. Experts estimate that its value will increase by 14% per year. Find the number of years it will take for the value of the guitar to reach 60,000. So our function, so the value over time of this guitar, and sometimes you'll see like a lowercase letter in the subscript, sometimes just used to describe what we're talking about. So VG of T might be value of guitar over time. So just be aware that that could pop up. It doesn't really mean anything when it's in the subscript. So bought it for 12,000 and it's increasing by 14%, so 0.14 to the power of T. We want to know the value of T when the value, or how much T is when the value of the guitar is 60,000. So now it has to 5x its value. So it has to really increase quite a bit. So we got 1.14 as our growth rate, and then T. Now, one quick hint for you. The rule of 72 is one that we see in investing a lot. So the rule of 72 is if you take 72 and divide it by the interest rate, that will tell you time it takes to double. So at the moment, if you invest in the stock market is averaging about 9% per year. So if you put $100 in, you would expect it to double to 200 in about 8 years, because that would be 72 divided by the interest rate of 9. So it would take about 8 years for your money to double. So just looking at this, I'd be like, okay, 14% growth rate, so 72 divided by 14 is 5.14. So it's going to take about 5 and a bit years to double. So if 12 doubles, it's 24. If it doubles again, we're at 48. So it's going to be somewhere between, I would say somewhere between 10 to 15 years is my guess. And the reason why I want to tell you that is I want you to start guessing and estimating, like, what do I think my answer should be? And that way you have an idea if you are on track or not. Because if you make a mistake in your decimals, like say, just for example, you did 1.014, like you just had a bit of a brain fart and you put an extra zero in there and you'd be like, it took me 100 years to get there. And you're like, that's not right. Something's not right here. That interest rate was too high. It should have been somewhere between like 15 to 20 years. Then you can go back and check your work again. All right, so we're going to graph this once more. So this time it's going to look something like, 12,000 is my starting point, and this thing is exponentially growing. I'm going to go up to 60,000, put a line in, and I'm interested to know, when does the value of the guitar reach 60,000? What is that value for T? So let's put in our calculator and see. So in Y1, we've got the 60,000, and Y2, I've got 12,000 times 1.14 to the power of X. Graph it. My window actually still works for me. Actually, does it? I don't need to go up to, I need to go up to 60,000. So actually I need to go higher than 60,000. I'm going to go 65,000. I want to be able to see that 60,000. I'm going to increase my X max to 30. All right, so got my lines in, and all right, they do intersect. If they don't intersect, you have to change your window a little bit just to see, like, okay, is there a place where they do intersect that's just off screen that I can't see? All so I'm getting T is equal to 12 years. So yeah, somewhere between 10 and 15, it was 12 years. So 2.28 years. Which, by the way, guys, if you ever find something that is expected to increase by that kind of value, that is a wonderful growth rate. So hold on to that kind of stuff. So for those of you guys who think you have some collectibles at home, check and see like, hey, what's the approximate rate these things are increasing in value by? And then how long should I hold them before I consider selling them? So think of things like baseball cards, Pokemon cards, other random collectibles. Like I doubt many of you have artwork at home or anything like that, but things that you guys own that might be considered a collectible. Just take a look and see like, okay, maybe this is worth holding on to. Like store it somewhere nicely, save it, and then check back in a decade and see what it's worth. All right, your turn. So you've got a couple of different pieces to this. You want to invest $1,000 in an S&P 500 index fund. So S&P 500 is basically an index is a group of stocks, and the S&P 500 is the top 500 biggest companies in the US. So you're buying a basket of stocks that owns things like Amazon, Apple, Netflix, Nike, Under Armour would be in there, Tesla would be in there. So you own a little bit of all of these. So you're buying $1,000 worth of this index fund, and it's expected to return about 9% per year. So how much would Megan have in 15 years? So what would her $1,000 be worth in 15 years? So remember we said at 9%, we would expect it to double in 8 years. So $1,000 will be worth $2,000 in 8 years. 15 years is almost another 8 years away. So I'm expecting this. So 1,000 doubled is 2, 2 doubled is 4. So I would expect it to be worth somewhere between 3,000 to 4,000. That's what I'm guessing my answer is going to be. So the value of the fund in 15 years is going to be equal to $1,000 is our initial investment, the principal, 1 plus 0.09 to the power of 15. You don't even have to simplify the R value. You can just leave it as 1 plus 0.09. Just make sure it's in parentheses when you do your type into your calculator. Because if you do 1 plus 0.09 to the power of 15, it will only apply to the 0.09 and you need it to grab the 1 as well. So just make sure there is a parenthesis around it if you're going to just do it all in one go. Otherwise, combine it and make it 1.09. So we got 1,000 times 1.09 to the power of 15. That's 3,642. 48. All right, now I realize I didn't say pause the video there. So if you didn't pause the video, pause it now and get the other two answers, and then come back and see how you did. All right, when will Megan's account get to a value of 3,000? So this time we want the value to be 3,000. So we know after 15 years it was 3,600. So that means that it's going to be less than 15 years. It's more than double, so it's going to be more than 8. So it's going to be somewhere between 8 and 15. So we know we have a ballpark at least. So 3,000, 1,000, 1.09 to the power of t. Graph both sides and then see where do they intersect. So we got 3,000 is one of our lines, 1,000 is another one, and it's 1.09 to the power of x, and then graph it. All right, second trace, intersect. So for me, it is t is equal to 12.74. Actually 7.5 when I round to the nearest hundredth. So I'm rounding to hundredths, mostly because if I was doing the financial side, I would also round to nearest hundredths. So just make sure you're being consistent in how you round. And that's years. So 12 and 3/4 years, so 12 years and 9 months. Megan wants to have $20,000 in 10 years. Now, this is an interesting one. So you're like, I know what my goal is. I know what my time horizon is. I know what the interest rate is going to be, supposedly. Remember, this is not a guaranteed thing. It changes every year. Like last year, the interest rate was actually 31%. this past, so that was actually 2019. 2020 was, I think, 15% or maybe 20%. So it was like higher than average. So 9 is the average. So it can be better, it can be worse. Some years will be lower, some years will be higher, but over a longer period of time, it rounds out to about 9. So now the question is, how much would she need to invest in the beginning that if she let it ride for 10 years, she would have 20 grand at the end? So we know what the output is, so 20,000. We don't know what the initial amount is, so I'm going to call that A. We know the growth rate is 1.09, and we know that we're going to leave it in there for 10 years. So this one, it's very easy to solve algebraically. We're going to get A in its own, so that means we're going to divide 1.09 to the power of 10. And that'll leave us with A. So 20,000 divided by 1.09 to the power of 10. All right, and I get A is equal to $8,448. And 22 cents. So if she put 8 grand in, 8.5 grand nearly, into the account, grows at 9%, in 10 years she would have 20,000. So that's another question I could have asked you is, if you have, say, 1,000, you want to turn it into 20,000 in 10 years, what kind of interest rate do you need to find to be able to do that? And then you try and see if you can get your investments to match that interest rate. That's the hardest one to do because there's no real guarantee for high interest rates. It's pretty much the higher the potential for growth, the more risky it is and the more potential there is for it to go the opposite way as well. So if you leave your money in cash, it holds its value. There's 0% growth, but there's also 0% loss. So it's fixed. If you put it in something like an index fund like the S&P 500, it's averaging 9% every year, but there will be some years that it goes down. There will be some years that goes up. You don't know that there isn't a recession coming around the corner. So you really only invest money when you know you've got at least 10 years for it to go down and come back up again and do its thing. And then you would expect after 10 years, you will have more than what you put in. And usually significantly more. All right, so compound interest formulas. These are some new ones for you that I do need you to know, and they're worth knowing anyway. So the first one is simple interest. This is like the most basic type of interest we have. So I is the interest that you would earn on a loan or an investment. P is the principal amount, so the amount borrowed or the amount invested. R is the interest rate, and T is time. Most common ways we see this are like, I give you a loan and I say, okay, I want 2% interest on this loan for every year that it takes you to pay it back. So, you borrowed $100 from me and I say, okay, 2% interest. So 2% of 100 is $2. And for every year, so you borrowed for 5 years. So for 5 years, you're going to pay me $2 for borrowing my money. And then at the end, you have to give me back the $100. So I would make $110 total. So that's very simple. The other one is what we call bonds. So bonds are pretty much loans that you make to the government or to different businesses. And we use bonds as a way of investing because they do pay a fixed interest rate. So you can loan the government $100 and they will say, okay, we'll give you 5% interest on your loan each year. And after 10 years, we have to pay you back your loan. And so you get paid for letting them hold your money each year for that 5 to 10 years, whatever it is. And then you get 5% back. So if it was $100, you get $5 every year for letting them borrow your money. And then you get all your money back at the end too. So you would come out, $50 ahead. So let's take a look at some examples. All right, the next one up is the compound interest formula. And this one is really when the interest is compounded. So that means it's calculated more than once per year. So if it's just once per year, flash up the values here. So the n value, the number of times compounded per year, is 1. And this formula just ends up becoming our standard. So P1 plus R to the power of T. So like the end value is 1, so they just disappear. So that's just your standard growth or decay model. But if interest is compounded on a more regular basis, so say monthly, this is a big example when it comes to things like your credit cards. So credit cards, they pretty much calculate how much you owe them, and they add interest to it on a monthly basis if you're not paying off your credit card on time. So you want to make sure that interest can work for you in terms of your investing. It can work against you in terms of your debt. So you always have to be very careful when you take on any form of debt, such as credit cards or loans or student loans or anything like that. So we're going to use this formula for calculating interest that is compounded more than once per year. So some words to watch out for. Annually is once per year. Semi-annually. Semi means half, so it's twice per year. Quarterly. So that would be every 3 months. So there's 4 of those. What else would be a good one? Weekly. So how many weeks in a year? It's 52. So it's 52 of those. Daily. If you see daily, don't do like 365 and a quarter. Just do 365. That'll be what the question is expecting. Bi-weekly. So say like you get paid or something bi-weekly. That means every 2 weeks. So that means there will be 26 of those in a year. So those are just some words to watch out for. In a word problem, for example, like you'll say like, oh, the interest is calculated quarterly, and all right, that means my end value is 4. So the number of times it's going to be compounded per year. And then the last one up is continuously compounded interest. Now, this is not one that we come across in like everyday life very often. It's used in the financial sector. It's used in like epidemics and other sorts of things where the interest, the growth is continuously happening. It's not like it waits for a certain point and then continues and then multiplies and then does it again. So we'll do some calculations with it, but it's not one you're going to come across on day-to-day life very often. So this is the PERT formula, my friend PERT, PE to the power of RT. So E is the natural number. So we came across this in our last lesson. So just make sure you know what the formula is and what each of the variables represents, and you're sorted. So if you get asked for continuously compounded interest, you know it's the PERT formula. If it's compounded monthly, I don't know if I put monthly in that last one. So monthly, remember, is 12. So if it's compounded monthly, it would be the last formula. And then if it's just simple interest, like there's no compounding going on, it's just a straightforward interest amount every year, then we would go for the simple interest formula. It should be indicated in the question, but you may have to read into it a little bit to figure it out. All right, let's do the first example. So for $1,000, you can buy a conventional bond. So remember, bond is an IOU. You are loaning somebody money, and a maturity value is basically they're going to pay you back the amount they borrowed. So at the maturity date, this is the amount they're going to pay you back. And in this case, they're saying they've got 4 years to do it. And in the meantime, they're going to pay you 5% interest on your money. So they're borrowing your $1,000 to help them grow for 4 years. And in that time, they'll pay you 5%, basically rent on your money. And then they'll pay you back your $1,000 at the end of the 4 years. So calculate the total interest earned over the life of the bond. So people you can loan money to, you can loan money to the federal government. So these are federal bonds, like you can loan money to the Treasury. You can do corporate bonds, so to businesses. You can do municipal bonds, so that's to your local governments or state level governments. And you can also do bonds to just standard people. So if someone has like a small business and they want to get a loan, they can do it through a bond market, or they can go to a bank and get a loan that way. Bonds vary in risk. So if you borrow from the US government, it's considered to be a very safe investment that you're very likely to get paid back. And then the opposite of that is what we call a junk bond. So that is a bond that has a very high chance of the person borrowing or the company borrowing it's not going to pay it back. But it also means you get to charge a higher interest rate. So I think if you do a treasury bond, like you might get like 2% interest on it. But if you do a junk bond to like, I believe Ford actually is a weird one at the moment that's like considered to be a junk bond. Like they're just not, very highly rated to pay their money back. It's kind of like giving a bond to Pennies or Macy's, like a business that you think is probably on the way out, those interest rates can go up as high as like 100%, 150%. So yeah, it varies. So the more risk you're willing to take, the higher the potential reward could be, but also the potential that you just get nothing back. All right, so this one is a bond, which is simple interest. So that is the I is equal to PRT. So this is just the interest, remember, not the total amount you're going to get paid back. So the interest that we would get, interest is equal to $1,000. The interest rate is 5%, so 0.05. And time, so it's not to the power of t, it's times t. So this isn't even an exponential formula. So time is 4 years. So how much money are you getting paid in rent for your $1,000? So 1,000 times 5 is 50 bucks. So you're going to make $50 per year on your money. So for 4 years, that means you're going to earn a total of $200 in interest on your money. So every year you'll get paid 50 bucks, and at the end of 4 years, you'll get your 1,000 back. Very simple. So that's why it's called simple interest. So there's no, the interest doesn't accumulate. There isn't interest on interest or anything like that. It's just a very straightforward agreement. A lot of times if you borrow money from like family members or something like that, you might have an agreement like this. Sometimes it would be, you will also accumulate the interest. So rather than paying $50 a year, we'll just say at the end of 4 years, you would owe me 1,200. So you're going to pay back a 5% annual interest rate at the end of the term. So you don't have to pay $50 a year. You're just going to, at the end, pay me back an extra $200 for borrowing my money. That's sometimes how it goes. It just depends on the agreement you have. So sometimes you get the interest paid to you every year. Sometimes you get it all at the end in a lump sum. All right, so this one. A person saves $200 in an account that earns 0.01% annual interest. Now that's a pathetic interest rate, but that is pretty much the national average for your standard bank. So Bank of America, PNC, like Capital One, like those are the interest rates that you are getting when you put money in a savings account. So how long would it take for your $200 to grow into $300 if it lived in a savings account? So now this one is an annual interest. So we're going back to just our standard growth decay model. It's really a compound model, but the end value is 1. So the principal is 200. The interest rate is 0.01%. So that's not even like our actual rate going into the decimal. So remember, as a decimal, that would be 0.0001. And then we want to know when the values of V of t is 300. So our formula, V of t is principal times 1 plus r to the power of t. So we want to know when it's going to be equal to 300. So this is one where you're going to graph it, and you're going to need a very long runway for x, because this thing is going to grow like a snail. So 200, 300, dot, 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 dot. So you will see this thing start at 200, and it'll look like nothing's happening, and it's just like taking its sweet time. So give yourself a long runway for t. If you're doing it in Desmos, you'll be able to zoom out very easily. If you're doing your calculator, it's going to be a little bit more zooming to get there. So first, y1 is 300, y2 is 200 times 1.1231 to the power of x. So yeah, like when my old window is still in my calculator and I can't even really see it at the moment. So I'm going to adjust my window. X max, I'm going to make it 100. So I'm going to see if 100 years is enough for this to happen. My X max, I'm going to put it back down to like 310. So zoom in a lot more. All right, so guys, 100 years is not enough at the moment. Oh gosh, what do we need to do? Let's do 1,000 years. It's like, oh, I'm starting to see some growth. So at 1,000 years, I'm starting to see like an exponential curve. Still not enough time. So window even bigger again. Let's go. I'm going to just go crazy. I'm going to go 10,000 years. See, is that enough? 10,000 years is enough. Okay, it's big enough. Second trace. Intersect. All right, so in a bank account like PNC or Bank of America or any of those, it would take 4,054 years, almost 0.85, so it's almost another year in there, for your money to grow by $100, for $200 to become $300. So not even to double, but to just grow by 50%. So this, my friends, is why you have to start investing your money if you want to ever achieve wealth. Saving it is never going to be enough. And I will actually add that inflation, so that is the cost of living, so how much everything increases in cost by, inflation is somewhere between 1% to 3% each year. So in fact, if you leave your money in a savings account, it's worth less every year because the cost of everything goes up. So for example, what $1 would buy you this year might cost $1.01 next year. So if you saved $1, you would no longer be able to afford something that cost $1 in 2020, because in 2021 it would cost $1.01, and your money has not even accumulated a cent of interest yet. So saving your money is a wonderful thing to do for things like an emergency fund, or just like saving for a short-term goal, like you want to save up to buy a car. But if you're talking about building wealth and being able to retire someday, or to pretty much like get to a point where you're like, I don't really have to care about money anymore, you have to learn how to invest your money to get it to grow. So once again, big pitch for a personal finance class or contemporary math, and ideally contemporary math, because I teach it and I think it's awesome. All right, let's go a new one. Person invests $1,200 in an account that earns 2% annual interest, and it's compounded quarterly. So now we're into that compound interest formula, and we want to find out when it has increased by 300, so it's worth 1,500. So just a reminder of the formula: V of t is principal 1 plus r over n to the power of nt, and n is the number of times it compounds per year. So at quarterly, n is 4. So V of t, so it basically divides the interest rate over the number of times, the annual interest rate over the number of times per year, which makes sense. Like if it's 2% over a year, then every quarter of the year you would expect to see about a quarter of that. It's a little bit higher because of the compounding part, but not much. So we got 1,200. Actually, that shouldn't be V of t because we know what the output is. So 1,500 is equal to 1,200 times 1 plus 0.02, so 1.02. Actually, I can't do that. I have to do the plus part. So 1 plus 0.02 over 4 to the power of 4t. So this is one where we will need to solve it by graphing for now. Next week when we do logarithms, we'll be able to solve this algebraically, but for now, this is going to be just a solve by graphing situation. So you'll have your 1,200 starting point, your 1,500 goal, and we'll see this thing grow, and we want to know when does it happen. All right, so in your y1 spot, we've got 1,500, y2, 1,200 times 1.02 to the power of, so yeah, don't forget your brackets here. So 1 plus 0.02 divided by 4 to the power of 4x. And you want to make sure if you're doing this in calculator that you are using parentheses here to tie everything together. So like you want a parenthesis around this, so that your calculator is very clear on what you are trying to do. And now my window is totally inappropriate for this, so I'm gonna have to change it. All right, so I made my X max 20, so see if it can be done in 20 years. And then Y max I set at 1600, so just higher than that 1500, so I can see when that point of intersection would happen. And looks like I gave myself enough time. Yep. So second trace, intersect. It ends up being 11.19 years. So 11.19 years. Now, if it's calculated quarterly, technically you would have to skip forward to the next quarter. So it'd be 11.25 years before you would actually cross that threshold. So like you would see as your money grows, it wouldn't be a smooth curve like this. It would be stays at 1200, interest calculated. So it jumps up, interest calculated jumps up, and like you would see it grow that way. But the way that our calculator does it is just a smooth curve. Totally fine. And I would accept 11.19, even if technically it's 11.25 before you see that. All right, we're going to do another one of these ones just because it's the most common one we're going to see. $600, 6.25% interest rate compounded semi-annually. So that is an end value of 2. Find out when it reaches 1700. So it's going to more than double. So it's nearly tripling. And 6.25% annual interest rate, but it's compounded a little bit faster. So I would still say the rule of 72 is pretty much going to apply. So 72 divided by 6 is 11 years. 72 divided by 6.25. Sorry, that was 12 years. So 6.25, so it's 11.5. So every 11.5 years, it's going to double. So that would be almost 3 doubling periods needed. So it would be, I'm going to guess somewhere between 20 and 30 years, probably around 25. All right, so we need 1700 is equal to initial amount invested is 600, 1 plus 6.25% interest, 0.0625. So put in all those decimal places, compounded twice per year to the power of 2t. Graph both sides. Let's find out when this is going to happen. So we've got 1700 on one line, and we've got 600 plus 1 plus parenthesis 0.0625 divided by 2, close parentheses. So I've got 2 closings, and to the power of parenthesis 2x. Adjust my window. I need to be able to see 1800, and we said somewhere between 20 and 30 years, so I'm going to go 30 years. Let's see how that looks. So when I graph it, I'm getting a straight line, which doesn't look right. So I made a mistake somewhere in my so I did 600 plus instead of 600 times. Here we go. So you'll notice when you look at your graph if something just doesn't look right. Okay, graph intersects, which is perfect. So t is equal to 16.9. So I was actually a little off there. I thought it would be between 20 and 30. Oh, I guess, yeah. So if it doubles once, it's at 1200. I don't need it to double again, so it would have been between 11 and 22. I had one extra doubling in my head. Or, yeah, 22. So 16.9 years. And this one is being compounded semi-annually, so that means you would go up to like the next half year. So really it would take about 17 years before you would hit that mark, but 16.9 is fine. All right, compound it continuously. So this is that value is equal to P e to the power of RT, our friend PERT. So value over time, we want to know when it reaches 12,000. Initial investment is 5,000. So it's going to be times e to the power of 3.5% annual interest, so 0.035 t. Remember, e is a value here. It's not a variable. So we're going to graph this again. So 1,200 is my one line, and then the next line is going to be 5,000 times, now e, you do have to find in your calculator. So it's superscript for the division sign on my calculator, so second function division, and then e to the power of 0.035x, and then close parenthesis. And continuously compounded interest will grow faster than annual interest. So the fact that it's being compounded more means it will grow at a faster rate. So if something's wrong with my window, let's see. Oh, I need to go up to 12,000, so let's go 15,000. All right, so it's growing, and it hits, perfect. So second trace, intersect. I wish you guys could see my screen. It's so much easier, but I've put in my lines. They intersect. I've hit the second function intersect button. T is equal to 25, and it's like 25.01 years. And this is something, guys, you can look up on YouTube again, like compound interest TI-84 calculator, or do it in Desmos. And I will go through these in our live class on Desmos so you can see what that looks like. This video is already going to be long enough without me trying to switch through screens or add in extra videos. All right, your turn. We're almost done. 4 questions. Pause the video, take a shot at each of them, come back, and we'll see how we did. All right, so that first one, Common Market. Now, this is actually a true story. Common Market in Frederick was raising money for its new location on 7th Street by issuing Class C shares. So remember, we talked about a share that's part of like the stock market. A Class C share, however, is kind of like a bond. It basically just says like, you don't own any part of the company. We're going to take it back after a fixed number of years, in this case 5, and we're going to pay a simple interest on it. So they were asking for $1,000 investment per share, so you could buy as many as you wanted, and they would pay a 4% simple interest on it. So if you're like, I don't need money, like I don't need this money for 5 years, and 4% is a heck of a lot better than I can get in a savings account, I don't really want to put it in the stock market. The only way this doesn't work out is if the common market like failed and wasn't able to pay back their money. So, which is always a possibility. There's always a risk when it comes to investing. But in terms of the level of risk, I didn't think it was that high. Now, my wife and I didn't end up investing in this, but we were definitely tempted by it. So let's see, you've got $1,000 for a share, 4%, 5 years that are going to hold it for. And we're just going to calculate what is the total interest earned for each share. So if you bought more than one share, you would just multiply your answer by however many shares you owned. So the interest is the principal times the rate times the time. So very straightforward one. So 1,000 times 0.04 times 5 years. So 1,000 times 0.04. So it's $40 per year times 5 is $200. So $200 would be the total amount of interest earned. And then after 5 years, they would give me back my 1,000 as well. So I would now have $1,200 instead of 1,000, which I started with. So it's not a bad deal. Like 4% almost guaranteed interest. It's great, but for my wife and I, we were like, we can do better in the stock market. So we can do better than 4% most times. And I'm glad we did, because we were investing this past year and we had almost a 30% return. So it's just a much better return in the stock market on average. All right, question number 2, person invests $1,000 in an account that earns 5.5% annual interest. So it's only going to be compounded once. Find when the value of the investment has doubled. Now you could use rule of 72 here. You could just say 72 divided by 5.5. So 72 divided by 5.5. It should take about 13.1 years, but let's actually calculate it and see what we get. So 1,000 times 1 plus 0.055 to the power of t, and we want that to be equal to 2,000, so when it's doubled. So 2,000 and 1,000 times 1.055 to the power of x. Second trace, 5 intersect. So it's 12.9. So 13, pretty close. I'm writing a dollar sign. 12.94 years. So the rule of 72 is like a rough guide. That's like approximately how long it'll take. So 13.1 versus 12.94, very close approximation. Number 3, a person invests $8,000 in an account that earns 6.5% annual interest compounded daily. Find when the value of the investment reaches 20,000. So 20,000 is equal to 8,000 times 1 plus interest rate 0.065, but compounded daily, so times 360 or divided by 365 days in a year, and then that's 365 t. So notice now, like, my exponent is going to be massive. So that's why, like, the more it gets compounded per year, the slightly faster it's going to grow. All right, so we're going to graph this one out. So I got 20,000 on one line, and I got 8,000 on another, and I got 1 plus 0.065 divided by 365 to the power of 365x. All right, graphing it out. Second function trace, 5. All right, so the time it takes is 14.09 years. And the last one, so 15,000 or 1,550, 4% annual interest compounded continuously. When does the value investment reach 2,000? So 2,000 equals 1550. Now this is the PERT formula, so P-E-R-T. So it's times e to the power of r, 0.04 t. So we got 2,000 on one line, 1550 on another, times e to the power of 0.04 x. I'm sorry for the pauses, guys. My calculator is not the fastest thing in the world. Desmos is much faster. All right, so I'm getting t is equal to 6.37. All right, so hopefully you guys did pretty well there. If you didn't, make sure you're asking me in the live classes, what do we do there? How does this work? Use office hours if you need to. Your Khan Academy this week is going to be testing you on all of this stuff as well. All right, so this is also posted in your Schoology folder. So it's the video on how to do the exponential regressions. So please make sure you're taking a look at that. Sorry, the title of the slide is totally wrong, but there's a video in Schoology that's going to take you through the regression lines. Make sure you take a look at that. All right, so essential questions. What does it mean when we say compounded interest? This is how often the interest is calculated. So the great thing about compound interest is that you get paid interest on the previous interest. So you have $100, it compounds at 5% interest annually. So after the first year, you have $100, you get 5% interest on it, you get $5. The next year, though, you get 5% interest on $105. So you now have 105 because the interest got added. You get interest added again. So now it's 105 times 5%, so you get 5% of that, and it just keeps growing that way. So you see the value of your money increase more and more and more, and the bigger the value of the money, the more the increase is going to be as well. So that's why we get that kind of L-shaped curve. So it starts slow, but then the value starts increasing quite quickly. The formulas for simple interest is I is equal to P times R times T. So no exponential stuff going on there. Compound interest, P times 1 plus R over N to the power of NT. So the number of times it's compounded per year has got to be included in there. And then continuously compounded interest is that PERT formula, PE to the power of RT. All right, after this lesson, complete the folder, Modeling Exponential Functions. Thanks for hanging out with me today and hanging through this. I know this was a longer video. Talk to you soon.